Okay, we're going to go ahead and get started this morning. We don't have a big audience at this point, but it'll pick up as people walk by and see what's going on. My name is Phil Stein. I'm with Guzzler Manufacturing. I'm a regional sales manager in Texas and Louisiana. Actually, I sell Guzzler vacuum trucks. Happen to have a customer in the audience that owns the one that's sitting over there, and he's from California, though. What I've done today, or what we're going to do today, is kind of give you a preview of some of the things that I do on delivery of a new Guzzler to help people understand what vacuum is, how it works, and the things that it does. One of the things that happened to me in Texas and Louisiana, things have been real good, quite honestly. Been a lot of sales, but you deliver a lot of trucks. They hire people that can drive a 13-speed Road Ranger, but they can't always operate a vacuum truck. And so what happens, you get in a situation where you start to have what you might think is a warranty claim on the surface, and really sometimes it's abuse or misuse, or they just didn't run the truck properly. So I put together this basic operator's training school, which only lasts about an hour. Here it's 4.5 hours when I actually do the school, has a test and what have you. And also we have a truck that we go over outside to relate some of the little demonstrations that I do in here. Some of the things that I do in here are kind of like a science or physics lab that you might have in school, and it's really interesting to see what happens with vacuum and how it works. So I'm going to go ahead and get started with some of the things that are really fun, and we'll have some fun with the audience, and you'll see some real interesting things that might help you in your business, hopefully. First of all, what is vacuum? Vacuum is negative pressure. What just about everyone in this room is doing with one size vacuum truck to the next size, from something this size to as big as a Super Sucker or the Guzzler or the Gap Vacs or whatever, we're creating a low pressure area. And in creating this low pressure area, what we're trying to do is move material from one place to another. So if we create a low pressure area, say in this jar, actually what happens is atmospheric pressure then pushes the material in the hose to the low pressure area. Kevin's going to help me today. He's going to help me do some demonstrations, and if he'll come around and come up here, I want to do something, this kind of basic, simple thing that we're going to start off with. What I'm going to have Kevin do, Kevin works with the Guzzler also, is I want him to blow this balloon up about this large, Kevin, and tie it off and seal it off. That's a little too big, won't go in the jar. What we're going to do, he has basically overcame atmospheric pressure with this balloon. So it's a little bit greater than the pressure in this room right now. We're, for all intents and purposes, about sea level here in Long Beach. So it's about 14.7 pounds per square inch. This is a little vacuum pump. I'm going to seal this balloon up in here, and I'm going to pull a vacuum on this jar. I'm going to decrease the atmospheric pressure in the jar. If I decrease this atmospheric pressure, what's going to happen to the balloon? Is it going to get smaller, or is it going to get larger? How many of you think it's going to get smaller? Okay, we got 2 or 3 people. That's about normal. 4. How many think it's going to get bigger? About the same. Most people say it's going to get bigger. What's going to happen is the same thing that happens with the weather. That's what makes the wind blow. There's high and low pressure areas all over the face of the earth. They're always trying to equalize out. I don't know why they never get equal, but temperature and several factors control that. So I'm going to turn this little vacuum pump on. It's a small vacuum pump, and pull a vacuum and watch what happens to the balloon. Well, I got to plug it in first. Got the wrong one plugged in. Okay, the pump's running. I'm going to seal off this little thing here. Can you see what's happening? I can't read the gauge from here, but it should be around 10 or 15 inches. 10 or 15 inches of mercury. Now what's happened now is the balloon is actually acting like a check valve on the little outlet here, so the balloon won't go down. There it goes now, it's leaking off. Basically that's what we're doing with vacuum pumps. We're decreasing atmospheric pressure within a vessel. And the greater or the faster we can do that, the better job we can do on certain materials. The little pump that this fellow has over here, he does in a school, is a rotary sliding vane vacuum pump. That pump in perfect condition will probably produce about 28 inches of mercury at sea level. It probably is somewhere around 200 cubic feet a minute. The Super Sucker, the Guzzler, or some of the other big machines in here use Roots type blowers, and they move about 6,000 cubic feet a minute of air at atmospheric pressure, 0. That's free air inlet volume. To compare what we're talking about here, this little vacuum pump here is a vacuum diaphragm type pump. It's a vacuum pressure pump. It would be closely related to this pump over here. The system here is just a shop vac. It's about 135 cubic feet a minute of air. 135, that's pretty close to what this little pump is over here. But it will only produce about 39 inches of water. The fan in here would be more related to the vac-on or the Vactor with centrifugal fans. I don't have a Roots blower. They're pretty difficult to get in small sizes to do the demonstrations and carry around. But I use this in my demonstrations to represent an air mover, and I use this to represent the liquid vacuum tanker rotary sliding vane type pumps. We're going to do a couple of demonstrations here that illustrate a couple of things about loading materials. I want to need another, Carlos, would you come up here? How did I get tied in a knot? Well, go down there with Kevin, I should have said. Stand on the ground down there. Yeah, down on the bottom there. Okay, what I have here is a couple of hoses we're going to use to lift some liquids with. But we're going to do another demonstration first that I need Carlos for here. We've got some rubbing alcohol here. Let's stand right over here, Carlos. Got some rubbing alcohol here. I'm going to, basically, other people have used this, so I'm going to sterilize it. That's all I'm doing with the rubbing alcohol, so that we don't get any contamination. Turn right. Can you bend over a second, Carlos? No, not really. That's not what I had in mind. but it is kind of funny. What I have is two pieces of 1/4-inch hose here. This one's about 6 or 8 inches long, and this one's about 8 feet long. And what I want to do is I want you to blow through the short one first, as hard as you can. Just blow through that hose. Now kind of remember in your mind what happened there as far as the force that it took to blow through that hose. Do it again just so you can remember it better. Okay, now blow through the long hose, hard as you can. Yeah, in your own words, describe the difference between blowing through the short hose and the long hose.
Well, this one is easier to blow than this one, and that one is, the pressure goes lower than the small one.
It's a tremendous difference, isn't it? You would not believe that it's probably 5 times harder to blow through a 1/4-inch hose that's 8 feet long as opposed to one that's 6 inches long. Now, what does that have to do with what we do in this industry? It has a lot to do with it. It's something called friction loss. The longer you have a hose, and I don't care whether you're pushing air through it or sucking air through it or you're pushing water through it or whatever, the longer the hose and the smaller the diameter, the greater the friction loss. This absolutely devastates the performance of all vacuum equipment when you have long, small diameter hoses. What we're going to do is a demonstration here to show you what happens with liquids whenever they're sucked through a hose. Now, you want to stand down there? Stand down on the ground there with him. What I have here is this Mazola oil, cooking oil, and this is water that's just colored with coffee. I want you to set both of these on the ground and take the lid off. And some of you guys in the back, you might want to stand up when we do this. Now I'm just going to hold this hose up. We're hooked to the same vacuum source, this bottle here. And I'm going to turn the vacuum pumps on, and I want you to watch the rate at which these two materials travel through this little 1/4-inch hose. Do you see where the water is? Where's the water? Okay, hold your finger in oil. It's still moving, isn't it? Okay, I'm going to let it go back down in a jar a second. Watch real close. It happens real fast. That's about the equivalent of 10-weight hydraulic oil, that Mazola oil there. The water's here, and the oil's right there for right now. Let's just wait a minute and see what happens. Now, see what's happening? I've got it pinched off here right now. So the vacuum's still equal on both hoses. Where's the oil now? Where's the water now? Well, what's happening here? Does someone want to explain to me what's going on here? Why did the water go up the hose faster than the oil? Well, what we're referring to here, the viscosity of oil is greater than water, meaning that it's thicker when we refer to viscosity. Once I pinched this hose off and the vacuum became static, the water went down to a lower level than the oil. Why is that? What would we call that? The specific gravity of water is greater than oil. So what would that tell you? That would indicate that oil would float on top of water. It also would indicate that because something is thicker, that it travels through a hose a lot slower. And again, these are equal diameter hoses. I'm going to change up a little bit what I did, and I want to do something similar to that, but I want to do it with a heavy material. This is just, let them take a second to drain that out, put the lids back on it. Now I want you to try. So the video can get it. But take this jar and this jar. Let me I'll show them something for a second. Can you see these look identical? They're really not. They have the same size inlet on both of them, but this is a 3/8 diameter hose. This is a 1/4 inch diameter hose. That's not very much difference in size. Would you agree between a 3/8 and a 1/4? Or can you see it back there? Can you see the difference? What I'm going to do is take those two hoses. I want you to hook one of them on here and one on there. We want to, and we're going to.
These hoses we use.
Yeah, just give me the end of each hose. There you go. You can tell Carlos has been in the field. He's already figured it out. And what we're going to do, this is just prepared mustard. I want you to kind of stand off the side and kind of hold those down in there. Can you stand off the side so the class can see it? And what I'm going to do, mustard would be a more equivalent to a heavy sludge than water or oil. And I want you to see the difference in loading rates in a 1/4 inch hose on this side versus a 3/8 on this side. And it's going to happen fairly fast. I'm going to try to hold these down in there. Can everybody see? Look at that. Even after I turned it off, it's still going in this hose over here. Now, what would you say the difference in the time it took to load that one? This one still hasn't loaded. It's the same material with the same amount of vacuum on both jars. This one's full. It's already going over into this hose over here. This one's still going. Now, does that mean anything to you as contractors, or would it mean anything to potential customers? It means a lot. You guys, as well as I, have competition. And you've heard of some guy going on a job, he's got a brand X truck one day, and he just did a super job. You go out there with a truck that's maybe more powerful. Send your operator out there, he does a job, and the customer calls and complains. But this other guy had a truck out there, and it didn't look very good, but boy, it just beat your new truck all to heck. He loaded up this sludge and stuff and was gone, and other guys fooling around all day. Well, I'm going to tell you what happened to him. He goes out there with a 2-inch hose, trying to suck some bunker oil or heavy type material, puts a 2-inch hose on it because it's easy to handle, and your competitor went out there with a 6-inch hose on it, and he loaded the truck up and he was gone while you're still fooling around. Now, that starts to make a little sense now why this is important, doesn't it? Because all of us want to do a good job for our customer, and you want to keep that customer. And then sometimes most of you people are management or owners of businesses, don't understand how could this guy beat me? There's no way. You didn't know what your operator did when he went out there. I don't sell hope. Well, we do, but I want to guarantee you that some of you guys are going to take a serious look at using larger diameter hoses and heavy materials. Basically, what we've been talking about here would relate more directly to a liquid vacuum tanker, such as several of them that you see in here, or potty pumpers with small pumps. Some of the new high-performance Guzzler, Aces, and some of the machines that you see in here have the 27-inch Roost blowers today that can run 27 inches continuously. And in heavy, soupy, nasty sludges, stick that 6-inch or stick that 8-inch hose on there. If you're competing with competition, and I see some of my competition sitting here, I hope I'm not giving away everything, but if you're competing with competition, put the biggest hose that you can put on there to get the maximum performance out of your machine. And I don't know how else I can illustrate it any more dramatic than what we've done right here. take just a second. We're going to try to clean this up the best we can so I don't have it all over me. Yeah. I'm going to set this back up. Okay, let me get them out of the way here. Some of these things I do are a little bit messy, and you got to take your time, or the next thing you know, you got mustard and everything in the world scattered everywhere. Does everybody understand what I'm talking about as far as friction losses, larger diameter hoses? Okay, we're gonna start talking about air movers and how they work. I got that thing on there so tight I can't get it off. I'm going to take this one here and set it off the side now, Kevin. Yeah. Air movers are really our basic business at Guzzler, as some of the other manufacturers here are our basic business. What I have here is a model made out of plastic that actually works. We'll fire it up here in a few minutes and let you see how it works. But all air movers have basically the same components. They'll have a tank, they'll have an inlet, loading port, some will have a boom, as ours, or different options as far as the way they load the material. The material goes into the tank. The tank becomes really one of the first stages of the filtration process, because as the air moves in at X velocity, it reaches a big tank and the velocity slows down and the material falls out of the airstream. At that point, what happens is the air comes out of the tank, goes through a cyclone. In the case of the Guzzler Ace, it's one cyclone. Some people